Mr. Penguin, I started studying fluid mechanics.
That's good. How is it going?
Actually, I'm in a trouble. Before I started studying fluid mechanics, this derivative was acceleration. But they say that this is acceleration in fluid mechanics.
Yeah. It's the material derivative.
What is the material derivative? What's the difference from an ordinary derivative? And what's the difference between these accelerations?
Okay. I'll answer the questions. First of all, let's review what this ordinary derivative is. We are seeing a ball flying. If we know what kind of force is applied to the ball, we can find out where the ball will be in the future by solving the equation of motion.
I think we can analyze the movement of fluid in the same way. If we know what kind of force is applied to a particle of fluid, we can find out where the particle will be in the future by solving the equation of motion.
Yes, you are right. However, unfortunately, the idea doesn't work. Because the number of particles is huge.
Then how can we analyze the movement of fluid?
It'll be easier if you analyze what's happening to fluid in certain positions. The positions are fixed in space.
How does it work?
At a certain time, each position has different fluid like this. And then we can observe, for example, their velocity. So, in fluid mechanics, a velocity is expressed like this. This means time, and this means position vector. They are independent from each other.
Okay. The idea is easy to understand.
That's good. So, let me give you a question. Have you heard of steady flow?
Well, does it mean all of the velocities are the same like this?
Actually, steady flow is not like that. The meaning of steady flow is that velocities don't change even if time passes.
Okay. If so, when we are seeing steady flow, the partial derivative of the velocity with respect to time is zero, right?
Yes, but do you know what this partial derivative mean? Do you think that this partial derivative is acceleration?
Well, I feel so maybe.
Do you mean that steady flow is not applied any forces?
What?
Considering the equation of motion, zero acceleration means that the material has no forces, right?
I don't feel that steady flow is not applied any forces.
The intuition is correct. Steady flow can be applied forces.
I'm confused.
Actually, this partial derivative doesn't mean the acceleration of fluid. I'll explain what this partial derivative means first. After that, we are going to go into the topic about what the material derivative is.
Okay. So, what does this partial derivative mean?
Let's say, fluid A has this velocity at a certain time. As I already told you, a velocity is expressed like this in fluid mechanics, since fluid mechanics is interested in a status of fluid, at a certain position, at a certain time. I define r1 as the position vector of this position. Then we can express the velocity like this. I'm going to use the velocity later, so I copy it on the side of the screen. What will happen if time passes by dt second? Since fluid A had this velocity, fluid A is supposed to move to this position. At this moment, fluid A has, let's say, this velocity, and the velocity is different from the velocity that fluid A had a while ago. If we define r2 as the position vector at this point, we can express the velocity like this. Please pay attention to this position again. At this moment, another fluid B came into the position. The fluid has this velocity, and as you know, the velocity can be expressed like this. Now, let's consider this partial derivative again. Will you describe the derivative?
Sure.
Thank you. Do you agree that the partial derivative means how much the velocity at this position r1 changes?
Really? Why can you say so?
Please take a look at these velocities.
The left velocity is the velocity that fluid B has now. And the right velocity is the velocity that fluid A had a while ago at the position r1.
Did you realize the reason why this partial derivative doesn't mean an acceleration?
Yes. It's because the partial derivative expresses the change in velocities of different materials. The partial derivative is something like the change of the velocity of a baseball, and the velocity of a golf ball, that comes into the same position where the baseball left. This derivative is not an acceleration.
You got the point.
But how can we describe the equation of motion in fluid mechanics?
That's the time when you make use of the material derivative.
How come?
It's because the material derivative observes one material like this. Let's confirm what's happening. First off, these velocities are expressed like this. Please note that these parameters are dependent with each other.
Why? You told me that the parameters are independent with each other in fluid mechanics.
Yeah, I told you so. But in this case, we are observing one material, and so the position vector means this blue line. The blue line is the position of the fluid we are observing. When we focus on one material, the position of the material is a function of time, right?
I understand that position and time are related with each other in this case.
So, the acceleration is described like this. If we think in two dimensions, we can describe it like this. Let me describe only x component, since there is no space on the screen.
I guess that we can apply chain rule to it.
Yes. Will you do it?
Sure. Done. Wow. I got the material derivative.
Yeah, now you understood what the material derivative is, didn't you?
Yes. Fluid mechanics doesn't focus on one material, but when we have to focus on one material, like in the situation where we describe the equation of motion, the material derivative will be the proper derivative, in the expression of fluid mechanics.
You got the point.
Thank you.